Hello all, welcome to my channel. In this video, we will see how to visualize a DC signal. Visualizing a signal is all about understanding how charges move in a conductor. So first we will see how charges move for a DC signal, and then we'll see the same charge movement for different sample waveforms, and finally we will talk about the importance of knowing how charges move in a conductor. So let's get started. The full form of DC is direct current. In a DC signal, the charges flow only in one direction. When I say charges for a metallic conductor, assume this to be a metallic conductor, and the charges here are electrons. Therefore, for a DC signal, this electron will only move in one direction, either to the right or to the left. Let's consider the simplest of all the signals, that's a constant amplitude signal. So you have a constant amplitude, say I, for infinite amount of time, t. At any given instant of time in a conductor, if this is the conductor, electrons at any point will not be at rest. They actually have velocity in all random directions. So the average velocity cancels out and the electrons can be assumed to be stationary. Okay, let's see what happens when you apply a signal like this to a conductor. We can assume this to be a signal for a current I, and current is directly proportional to the drift velocity of the electrons. So you can also think of this as velocity versus time graph for a electron. So let's take an analogy. Suppose you are on a road which does not end at all and you are in a car. Okay, and you are stationary, so your velocity is 0. Now suddenly you jump to a velocity of 60 km per hour and start moving in this direction forever. That is what the electron will do when you apply a signal of this nature. The electron, which is at rest now, will start moving indefinitely in this direction with a constant velocity v. If you had a car and you wanted to reach 60 km per hour, can you jump directly from 0 to 60 km per hour? No, you can't do that. The only way to reach 60 km per hour is by going from 0 to 60 in some time t. And then you can maintain that constant 60 km per hour for an indefinite amount of time. That is true for electrons as well. Electrons which are stationary inside the conductor cannot directly get a constant voltage V and move in one direction. They need to gradually increase their velocity until they reach their desired velocity, and finally they will keep it constant to move in one direction. Therefore, whenever you write a waveform like this, it is impossible to achieve it practically, as we just saw now. Always the electrons need some amount of time to reach the velocity v, and then they start maintaining that velocity in that direction. If you have a DC signal like this, with velocity versus t, for all these time periods the electrons are at 0 velocity, and again they are at 0 velocity for this time periods, and between these two time periods they have a constant velocity, say capital V. And now let's visualize this in a conductor. You have an electron which is stationary, This is t1 and this is t2, and now it has to move in a constant velocity between t1 and t2. So electrons which are at rest will be at rest until t1, then they will start moving at a velocity v and finally come to an halt at time t2, and the electrons will be again stationary at this point. As we discussed before, electrons which are at zero velocity cannot directly uh, get a constant velocity of v, so they have to gradually increase from 0 to v. Therefore, the practical waveform which you would get for this would be something like this. An electron which is at rest will take some time to reach this velocity v, and then it will be in that velocity for the constant given amount of time, and again it has to reach 0, so it cannot reach 0 directly from that velocity v, so it will gradually reduce its velocity until it becomes 0. Let's see one more DC signal. Suppose you have a triangular signal like this. This is a DC signal too. This is the velocity of electrons, or equivalently you can think of it as a current. And when you are given such a waveform, how do you visualize the movement of charges in the conductor? This waveform only signifies how the velocity of the electrons vary in the direction of the motion. So if the electron is in at this point and it want to reach this point from A to B, this waveform only shows how the velocity of the electrons vary when it tries to move from A to B. So in this case, for this part of the signal, the electrons will increase their speed and reach some distance. For this part of the signal, the electrons will decrease their speed and reach some more distance and come to an halt because the velocity becomes 0 here, and they keep on repeating this: increase the speed, decrease the speed, come to an halt, increase the speed, decrease the speed, and finally come to an halt. So probably the next question that comes to your mind is, then what is the difference between a signal which does this and a signal which does this? In both the cases, the electrons increase their speed until the midpoint and again decrease the speed until they become 0, just like what we discussed in the previous example. But what is the difference then? The difference comes in how the speed varies with time. In this case, the straight line indicates that the velocity of the electrons increase linearly with time, and in this case the electrons try to increase their velocity quickly in the first few seconds of time, and then later slowly increase the velocity at the end. But in the first waveform, or this waveform, the electrons uniformly increase their speed as time passes. So that's the difference you can visualize when you see a waveform like this. So let's see one final example, probably the most common example which you've seen is a square wave. These square waves are widely used in clock pulses for microcontrollers. So how do electrons move in this case? You have a conductor, you have electrons, T1, T2, T3, T4 and T5. Let's assume this constant velocity to be some v. So the electrons move with a constant velocity v for some time t1, and then they halt here until between these two times, and they again move with a constant velocity v between t2 and t3, and they again halt. They'll halt for t3 and t4, and they again start to move with a constant velocity v the electron just moves, stops, moves, stops, moves and stops. As we discussed previously, electrons which are at zero velocity cannot directly jump to a velocity v, so they have to gradually increase, then maintain that constant velocity v, and then gradually decrease to zero. This is an ideal waveform, and a practical waveform would look something like this. Probably this is what you would have seen in most of the textbooks, and now you understand why this small delay comes in the picture. I hope this video gave some understanding on how charge carriers move in a DC signal. This will be very helpful when you solve complex circuits and analyze how signals behave with capacitors and inductors. In my next video, I'll give an intuition on how charges move in a AC signal. So that's all for this video. Thank you.